today we're going to do section 3.1. So first let's look at the book. All right. We haven't scanned this page yet, so this is the full page. A little closer or something. Why is my page not paired? Okay, maybe like this. Okay, and then the top of the page and the bottom of the page. Okay. Next, page 90 and 91. Let's see. All right, that a little closer. That should be it. Okay, and then focus on the top of the page and then the bottom of the page. Okay. And finally, the last scene, 92 and 93, I think. Okay, that should be it. All right, and then a little bit on, focus a bit on top, and then focus a bit on the bottom. Okay, that should be it. Now, so we're starting a new chapter, which is very exciting, but that's not what I'm excited. I found something in the grocery store yesterday, which is very exciting, and I want to show you right now. Check this. What's this thing? It is a Millennium Falcon gingerbread kit. Isn't that awesome? And when you show you the back, see? And yeah, it's a pretty simple thing, but it's neat, okay? And the side of the box, and so on. The top and the bottom look about the same. So anyway, I just want to show you that incredible find I got at the grocery store. So having said that, let's start. Okay, so we're on page 88. Oh, before we start, there's something I have to show you first. That is, the concepts we're going to learn about today, you've already learned this in Calculus 3. Okay, I took a screenshot of what you learned. Now, if you don't remember any of this, that's fine, because we're going to develop all these ideas from the ground up. The reason I'm showing it to you, however, is to so that in case you remember some of it, and then you're wondering, have I had this before? And this is why you remember it. Okay. And first concept is the principal unit tangent vector. Now, if R is the position vector, then the tangent vector is defined as R prime over its magnitude, which is why it's a unit tangent vector, is being divided by its own magnitude. Next, the arc length formula is something like that, right? It resembles the Pythagoras theorem, of course, which can also be written as the magnitude of R prime. And the functions inside all have derivatives, which you might remember how hard it is to do the arc length. And next, we another way of saying arc length, the arc length function. Now, this is the formula, that is, you are integrating from a to b. This is just the function. That is, we are integrating from a to t. So s of t is the arc length formula, then is equal to the derivative of the vector r. Integrated, and you calculate the magnitude. In other words, is this thing. Okay, that's the same thing, basically the same thing. And there are a couple more points I want you to refresh your memory. That is, ds by t dt from this formula will be equal to r prime of t's magnitude, which is always bigger than 0. And also, if it is equal to 0, then see what I underlined in red here. The parameter t represents the arc length. Okay, and so that, so all that, you don't need to look any of this stuff up if you don't remember it. The reason is we're going to talk about all this stuff today from the ground up. So if you never heard of it, that's fine. It wouldn't matter that much. But I just want to remind you of the good old days in Calculus 3. Okay, so let's now go to page 88, where we talk about, see, arc length of a space curve, exactly the same thing. And we're going to build this case. Basically, we're going to reinvent the wheel. So let's look at this. Okay. First, the arc length, we're representing the vector as x of t. Okay, which is a vector, so it has 3 components. Because we're talking about 3D right now. And then we're going to define something. We'll split there's a interval of t, and we're going to split it into a bunch of finite intervals from t0 to tn that goes from a to b. And then we'll define this delta as the maximum of all the intervals. So we cut them into random intervals, but delta will be the biggest one of them all. And then the length of the arc, excuse me, the length of the arc then is defined as the limit of of each tiny little segment as added together as well, that is the magnitude, okay, as delta goes to 0. That is the biggest difference between all the t's has to go to 0. And this, if this limit exists, then the total sum, the limit, will be called the length of the arc. The curve is then has a name for it. It is called rectifiable. Now the English word rectify means to correct, okay? And well, why are we calling this rectifiable? It's just a mathematical tradition. So let's so try to remember that. Rectifiable means the length of an arc can be calculated. That's all it means in math, anyway. So let's look at the next page. Now, if we have a certain vector, okay, and then the vector is going through some point from A to B, and it is the curve, the resulting curve is rectifiable, then it will be given as the integral of x prime t dt, which is what we learned earlier. However, we're going to prove this, and the way we're going to prove it is by coming up with this formula right here, because by the law of the mean, okay, then this thing down here that we saw earlier, this thing, okay, is going to come up to look like this. Now, why is that? So please write this out yourself to see why this is the case. Now, here's what I wrote out. Okay, so this is the limit, okay, and then being that it's the sum of the absolute value of two vectors, then I wrote it out the old-fashioned way. That is, their components squared and take the square root, all that stuff. Here's the square root right here, okay, and then so then we consider each component. At this point, we'll take the good old mean, the oldest mean value theorem. That is the one that's applied for 3D functions, I mean for 1D functions only. And then apply it to each individual component, which then gives us some kind of x prime for each component, okay? So then apply the MVT, it gets me this thing, okay? The difference of f of b minus f of a is equal to f prime of something times b minus a. So then when I add them all, when I add up the magnitude, then this equation actually makes sense, is how that works out. So please work this out yourself as well. And as a result, we are able to come up with this limit, okay? So that's where the law of the mean got applied. It applied to each one of the components, and then add it all up. And then we remember that from this limit, we can then derive the definite integral, which is defined, well, loosely speaking, from basic calculus. That is the integral from A to B, okay, of all the stuff inside dt. Now, your book mentions that we're going to prove this process rigorously later, okay? But for now, we'll just remember what we learned in basic calculus and use this theorem anyway, without having proved it yet. So then this, of course, then equals to the next theorem. Let's see, okay? Now the next thing, and that is the length. And the next thing we are going to do is the arc length. Now the arc length, of course, is defined as from t0 to t of x prime dot itself. And that is what this means, right? And the magnitude of x prime is something dot itself, is the x prime dot itself, then you take the square root. That is the same as this, except that now we're writing s as a function of t. But we're using the same dummy variable. In your book, this function is defined with a different variable because that is how you're supposed to do it. okay? Because, I mean, see, the old definition of the arc length function is defined with a different variable. The dummy variable is different. But now we are in advanced calculus, and we are not going to even bother with that. We'll just assume that you know that, okay? And the integration is just going to be written down like this, period. Even though we know that this t and the t on top are two different t's. Anyway, so that equals to, so when you take the derivative then, is ds by dt is the magnitude of x primed, the derivative. Or put it another way, is ds squared is equal to all the derivatives squared, or can even be written to like this. And I have this thing written down in a slightly different way, but it's the same principle, okay? So please write this stuff out yourself as well to see how all this stuff makes sense. So after you write it out, then that's where we got that thing. All right. And so next, let's look at, and of course, notice that s increases as t increases because s equal to some kind of integral of a positive value, okay? The magnitude of something is always positive. So s increases as t increases, okay? And it even has a name for it. The direction of increasing s is called the positive sense of the curve. How cute. All right, so bear that in mind. So first we learned rectifiable, and now we learned the positive sense. Which I don't think was mentioned before in basic calculus. So let's move on to look at example A on page 89, where we have a very simple helix. Okay, and we're going to plug in the formulas we have just done to just take a look at it. So first we know the helix. We'll take the x prime, which is x1 prime. That can be done very quickly in your mind. And then eventually, if you continue to do it quickly in your head, you realize the x prime, the magnitude of x prime, is a constant of square root of 2. And so therefore s, you can be integrated very easily. Now normally, s is extremely hard to integrate, okay? Because look at the formula of s. You have 3 squares and then have to take the square root. But if what's inside is a constant, of course, life becomes much simpler, and s is just square root of t. And so then as a result, we can plug in s instead of t in the original function. The original function has t as the parameter. We'll use this relationship to put s in there, okay? So now t is s over square root of 2, and then we have this representation. And so now the function is being represented by the arc length. The parameter isn't just any old thing, it's actually specifically the arc length. And that matters why. If, as we have mentioned before, well, we'll talk about that later, okay? And let's move on. So the positive sense is what makes the x3 coordinate increase. Well, whatever. So please read that carefully, okay? And then I'm moving on to page 90. Let's look at theorem 1. So next, let's look at page 90, theorem 1, which says that the parameter t in the arc length of the curve equals to 1 if the parameter is the arc length if and only if the x prime equals to 1 identically. Now the proof of this is extremely short, and so please go over this yourself, okay? But I'm going to talk about it briefly. It's so short that it might even sound confusing. That is, suppose that t is the arc length. That means that would mean that t is t minus t0 is equal to s, which gives you ds equal to dt, which means ds by dt equals to 1, which is x prime of t, therefore x prime of t is 1. Now conversely, if x prime t equal to 1, then we do the integration in the previous page, okay, which gives us s equal to as t minus t0. I'm talking about the integration. Let's see, did I even write it down? I guess I don't see it here. Well, it's on the previous page. That is the definition of s, okay? If the x prime, that is what's inside, is 1, then you solve this integration. That gives us s equal to t minus t0, and which means s is the arc length. So when it says the arc, it means the arc length. Okay, so theorem 1 is proved very quickly. Well, if that sounds confusing, please just read it slowly. Okay, it's harder to explain than to just understand, I think. So anyway, let's go on to example B, where we have some curve, okay, which if you were to calculate it quickly in your head, you notice the magnitude is identically 1 for the derivative. That is, x prime of t, the magnitude is identically 1, so therefore the t in here is the arc length by theorem 1. And then of course the curve is some circle where x1 equals to x2 in the x1 equal to x2 plane, centered at the origin and has a unit of 1. All that can be easily verified. So please do so yourself, and we'll move on to the next part, subsection 1.2. So section 1.2, we are going to represent the curve, that is the parameter, with the arc length as the parameter. And then next thing we are going to consider is the tangent vector. Definition 1. The tangent vector is a unit vector, alpha, and then in the positive direction of the tangent at the point that in question. Okay, the positive sense is what we mentioned a little earlier, where the s is increasing by the representation of this vector function. Now the tangent, theorem 2, the tangent vector to the curve is x prime of s. Now this derivative is taken with respect to s, okay, not t, and that's important. So therefore, and as a result, we're going to prove that this thing is not just a tangent, but that it has the magnitude of 1. Now to prove it, we'll consider s be a point on the curve. So s plus delta s is a neighboring point, right? And then we do the subtraction s of s0 plus delta x minus s of 0 is a direction that goes in the positive sense because s is increasing. Now if we then divide by the positive number delta s, which is just a number, it's not a vector, then we change its length, but as delta s goes to 0, the vector then of course approaches the x prime by the definition of x prime, which is going to be a unit vector. Why? Because we just had theorem 1, okay? Because the arc is the parameter, and theorem 1 on top of this page says that if the parameter t is the arc length, then x prime equals to 1, and therefore this tangent vector is a unit vector as the definition states, and that is that's about it. That is the proof that the tangent vector is x prime of s. That's very important to notice that the derivative here is taken with respect to s, not t. Okay, t is any old parameter. S is specifically the arc length, also called arc here in short. So let's look at the next part, okay? Now if the parameter isn't arc length, if it's just some random t, then the tangent of course still points to the tangent vector, okay? It's just, but the tangent that you calculate from x prime t, that is not necessarily 1 anymore. It could be any old thing. However, it is related to the x prime s in this way. That is the dt, the dx by ds, which is what alpha is, right? Alpha is taking the derivative of x with respect to s. Now that is end up being equal to dx by dt times dt by ds, which end up being dx by dt is x prime t, whereas dt by ds is the magnitude is 1 over x prime t. And that's from the certain previous formulas that we have done earlier. I wrote it out a little more here, see? And then the dx by dt, of course, is x prime t, but dt by ds is 1 over the magnitude of x, because we wrote it by equation 4 in the previous page. Because in equation 4, we wrote it as ds by dt. So we're going to flip it around and call this, okay? So that is That's where that comes from. Now, equation 7 is much more useful because from basic calculus, you might remember that nobody does dx by ds. I mean, taking derivative with arc length is a total pain, okay? And whereas taking derivative with some convenient parameter t is much better. So all you have to do this is take some random parameter and then divide it by the magnitude of x prime, which is still not necessarily simple, but is much better than messing with the arc length. So let's now look at the next page. That well, of course, in this situation, we assume the x prime of t is not 0. Otherwise, this is not going to mean anything. Now, when the cases where x prime t is not, it does equal to 0, we call those things singular points, and which we mentioned earlier, but this might be a different meaning. But in any way, we're not going to talk about it right now, okay? That's what excluded from discussion means. Now, try to memorize that phrase. If you don't want to talk about it, something, you don't say, I don't want to talk about it. You say, the topic is excluded from discussion. And that sounds much fancier. Anyway, so next, we may now, okay, now we're going to write down the equation for the tangent line. That is the line that's tangent to that curve we're talking about, and the normal plane to the curve. Okay, the normal plane is the plane that's perpendicular or orthogonal or something. Okay, and so the curve is going this way, but the normal plane will cut it at the right angle like that. All right, so here's the equation of both items. At a certain point, then the tangent line, of course, is by the equation of any old line, is we'll write the big X as the variable, and all the rest of the stuff is just constants except for the t, the parameter. So the tangent line's equation will be x of 0, s is 0, plus t times x prime s is 0. Now notice that if instead of taking the derivative with respect to s, which is hard, you can just replace it with the x prime of t. That will work just fine. That's because we're talking about parametric things here, okay? As long as we get the direction, we don't care how long the x prime, that is the vector is we just need the direction. And if what I'm saying is not that clear, it will become clear when you do homework. Similarly, for the normal plane, we're just taking the dot product of the difference times the x prime of s. So again, the magnitude of x prime of s doesn't matter. So you can just use x prime of t and it'll work just as well and much easier to come up with most of the time. So then, so that's what we're going to be doing. Now, so next, let's look at example C. Where's my example C? Okay, so example C is, we have a sample. We're looking back at example B, which was whatever that was, a circle or something. And we're doing the tangent vector at some random point, t equal to pi over 4, which if we plug it in, we have various values for the point, and also for alpha, that is what is the actual tangent vector at that point. And if you plug stuff in, then things will come out. So please do this example yourself, okay? And then it is, of course, something is perpendicular. Well, the tangent is perpendicular to the point itself if the point comes from 0. Well, in this case, that's only because this is a circle, okay? So that would be. And then the tangent line, you can work out the equation for all 3 parameters. And then the normal plane, of course, can be worked out the same way. And the normal plane happens to pass through the center of the circle because we're talking about a circle here. Now to let's see, okay, so please work this out yourself. Here's where I worked it out, okay? I calculated x prime t, calculate what alpha is. Alpha is x prime t in this case because something is the x prime t is, the magnitude is 1, so I don't have to divide by the magnitude. And then show that the dot product equals to 0, which means they're perpendicular. Okay, next, on next page, continuing. We have, so I wrote down the tangent line following the equation. Okay, we're going to write this stuff out word for word. Here's the normal plane. Well, I didn't write down them in 3 different components, but it's pretty easy to see here because it's a simple example. The normal plane, similarly, you plug in all the numbers with your big X. Remember, the big X is contains x1, x2, x3. Okay, when you take the dot product, which if we write this thing out, then as well, for one thing, if you write it out, it becomes a bunch of numbers and you end up with this thing. And also you notice that origin happens to be on this plane. That's because anything that's normal to the circle will cut right through the center of the circle, as is proved in elementary geometry. So with that, we have come to the end of this section. For homework, please do, there's a bunch of homework, okay? Please do problems 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, and then 14, 15, okay? And then, so to do the homework, you just have to, well, do quite a bunch of algebra, basically, and plug stuff in and remember which plugs in where. And of course, don't make any mistakes. So please go do your homework, and when you're done, I want to talk about some of them. I mean, all of them. So let's look at homework problem 1. Now we're on page 91. Anyway, so problem 1, we're supposed to find the parametric representation of something, I think. Okay, and x1 is equal to a, and then as a result, we have so we have x2 plus x squared plus x3 squared equal to 3a squared. And whenever we see something like that, we know it's a circle of some sort, and we'll slap on the cosine and the sine, okay, like this. And therefore, we can take, next we'll take the derivative and realize what x prime t is, and then pull out the definition on page 89, and to write down s, which is this integration. And then once you, so what is s x prime dot s x prime is end up being, when sine and cosine squared becomes 1, we got 3a squared. So, and then we take the square root, so we have square root 3 of a, which then end up being this particular value, okay? And that is the, well, we're talking about a circle here, so that's the diameter, calculated the integration way. And to check it with basic geometry, it equals to 2 pi times r, and r in this case is square root 3 of a. Yeah, so then because of this, okay? So then the diameter, so the geometry does check out, and that's problem 1. Next, let's look at problem 2, where we're supposed to figure out, find the arc length of some curve, okay? So let's do that. Problem 2, to find the arc length, we follow the formula. We have a bigger, we need to figure out what x prime is. Then we figure out what x prime dot x prime is over here. So we take this integral of this thing as square root, okay, and which end up being a neat little thing, okay, because the book is being easy on us. So then we can integrate some quickly and come up with some kind of answer that, if I'm lucky, this should not have any mistake in it. Although, yeah, I don't know. I'm not promising anything, but if there's a mistake, it shouldn't be a big deal. It's just as long as you follow the formula, that should come up with the right answer. So the next thing, this is what, problem 2. Okay, let's look at problem 3. We need to put the arc S as the parameter of this thing. We have a bunch of t's, so we need to change the parameter from t to s for problem 3. So I should write down that we're now on page 91, the homework. Page 91. Anyway, problem 3, to do that change, we're going to go through a process, okay? So here's the original problem. We calculate x prime of t, we'll follow the formula. We'll find the dot product and then write down follow the formula. S is then equals to from 0 to t or something like that of this complicated integration. Now the integration, however, luckily is able to take the square root the way it works out. It turns out to be a perfect square. So you can take the square root, and that end up being something that's easily integrable. And so then once the integration was done without messing up, I apparently messed up here. I don't even remember how. Now, anyway, so the point is, if you don't mess up, then we got to this point, which s equal to this representation. Now, what is then the next point is we need to pull t out of here, okay? Right, that is, we need to write down t in terms of s. Now we can just do it by hand. That is not that hard to do, or we can take a shortcut which is not much of a shortcut, and recognize that this is the sin h, that is the sinh function. Okay, and then the sinh function has inverse function. So I wrote down the inverse function right here, which I found online. I didn't want to bother doing it by hand, but it's not hard to do. It's just a quadratic formula that you can pull the t out of here rather readily. So, and I'm sure you've done it before in homework problems and stuff. Okay, but in any case, when we plug it in, then t in terms of s is this formula, which turns out to be the natural log of that pile of stuff. And then, of course, x is 1. Okay, now we have to go back to x1. What's x1? x1 is e of t. So you put that e in, then e cancels out the natural log. So x is in x1 is represented in terms of s without any log or e in it. Okay, so similarly, x2 and xt are similar. 3 are similar. Of course, x3 we need to leave the natural log in because there's no e in there. And I also took a quick picture of how to find the inverse function of the sinh is the sin h, that is, because I don't remember that ever being taught in basic calculus. I could be wrong though, because the problem isn't hard. And I just want to show this to you real quick. So if you have sinh x, right, and I want to pull the x out in terms of the other thing, let's say sinh x equal sinh of u equal to that thing. How do you pull the u out? So what you do is you end up applying the quadratic formula and everything comes out right away. You don't have to look at this very hard. It's just it's just a quick short problem, and that you can do well with or without this. Okay, but I just want to show this to you since I did find it. Next, let's look at problem 4, where we're supposed to find the equation of the tangent line and the normal plane for the curve in problem 2. Okay, so we'll go. So I went ahead and followed the formula like it says, right? Alpha, of course, equal to x prime t over x prime t magnitude, and then x prime of t is this thing, which means alpha is that thing, I don't know, divided by its magnitude, etc., which is fine. And then just based on that alone, I'm able to figure out the tangent as at some point equals to this thing. Okay, and I don't even think I need to divide by its magnitude necessarily, but I wrote it that way, I guess, which is all right. Yeah. Anyway, and then the equation of the, what is that? Oh, this is the tangent equation, which equal to that thing. But like I said, I don't think dividing by its normal is required. We can just go without. But I followed the plan and did dividing by the normal as well, as dividing by the magnitude as well to make a unit tangent. Anyway, but that is not necessary. Okay, just x prime itself is good enough. Similarly, the normal plane is the dot product, and I wrote everything out, and that is the answer. And when I was done, I thought, there are a lot of numbers here. I don't know. I don't trust myself. I mess up a lot. There could have been something wrong in here, and I wouldn't know it. There's no answer at the back of the book, which I think the answer at the back of the book gave the answer for problem 1, which is obvious. You don't need the answer. And then problem 4 would be helpful if I had the answer, but I don't. So what I did is that I check out a sample. I let t0 equal to 1 or something. Okay, at the point, which is the point that we're considering the tangent and normal plane of. So I chose t equal to 1 as a convenient number, and then I plugged things in to check what it looks like. Okay, so I calculated what if t0 equal to 1. So here's the tangent, and here's the normal plane, which I even wrote out the equation after doing some basic calculus stuff. Okay, I got this equation, and then and of course, this is the original curve that was given to us. So once I got this information, then I plotted it into the Desmos 3D calculator. See, here's what it looks like. Now, and then once I plotted it, then everything does look right. Now, here are my points, okay, as my random point. And you notice that the tangent line does look like a tangent, so that's good. And the tangent and that plane right here that I have, can you see it? Okay, the plane right here does seem to cross it at exactly 90 degrees. It's not as obvious from here, but if you are to to type this into a Desmos calculator yourself and then move it around, then you notice that it really is in 90 degrees. And there might even be a way to confirm it. I was satisfied enough at that point, didn't want to go any further. But that is how I'm comfortable to think that I actually didn't make a mistake in this case. That this, all these symbols I got, look at this. This is the first time I try it, and I did not mess up, which is totally awesome. Okay, sometimes I impress myself. So that's problem 4. Next, let's look at problem 5. Problem 5, did I say problem 5? I mean problem 6. Yeah, problem 6. Let me fix that. Okay, now problem 6, we have 2 curves, okay? They intersect at some point, and we need the angle between them. In other words, the angle of the tangent line at the intersection. So we're gonna, we've done things like that. That sounds familiar, but doesn't matter. We're gonna do it like we're supposed to do it here. And so we have, first we have these things, and we have to do the parametric representation. And so I tried different ways of representing it, and I think I settled on this one or something. Doesn't matter which one you represent, they're not that different. So and then as a result, I calculate A prime, right? Well, I call this set A, so then A prime, that's, anyway, the tangent A prime is, by the time I'm done with the derivatives, it looks something like that. And then at t equal to 1, all right, t equal to 1, then equals to the 2, 1, 1 of 2, 1, negative 1 over there. And then I was able to write down, this is the tangent line for that. And then at the other equation, similarly, I'm able to write down the tangent line, okay? And then I calculate the cosine theta, which is those 2 products, the dot product divided by the magnitude, which then I messed up, as you can see. But eventually I got myself out of the mud and was able to come up with the right answer if you do the dot product correctly, okay? Which is a very simple thing, but somehow, I got lost. But I found my way back and was able to get the answer at the back of the book. So that is the answer. So next, let's consider problem 7, where we're supposed to find the tangent line and normal plane to some generic equation. That is the very first equation in this section. Therefore, so we'll do that. Okay, we'll just write it out, and here it is. There's a lot of symbols that, but if I didn't mess up, it's all just straightforward algebra. Okay, so that's problem 7. And then next, let's look at problem 8, which says that for a curve that is this intersection of 2 cylinders, okay? So then we will, do that. So that it happens to be the intersection of 2 cylinders. Well, that makes it easy enough to do the parametric representation. We'll let x1 equal to t, and then x2 and x3 then will be f of t and g of t, and we'll plug everything just like it says. So very soon the tangent and the normal will come out, nicely. Okay, this is about it. And this is going to be useful for the next problem, I believe. Okay, next, let's look at problem 9, which says that we're going to call this thing as f x1, x2 equal to 0, and same for g. Now in that case, that is problem 9, okay? So problem 9, being the f and g functions, we'll assume that we can pull out x2 out of the function. It's so that x2 then equal to some function of x1, and x3 is some function of x1 as well. Now, the possibility of this is from the, what is this, the implicit function theorem, okay? That for 2 variables, which we have done on page 56 of your book. Remember good old theorem 14 from chapter 1, where you have a function, okay? And then the partial derivative of what you're trying to pull out of cannot be 0. And if that is the case, then you can yank the function out. That's what theorem 14 says. And therefore, we are going to do that. So assuming that is true, which means we have to assume the f2 and the g2 are not 0, okay? And then the answer, once that's done, this is the exact same problem as problem 8, see, identical, and therefore the answers are also exactly the same. So that's problem 9. Okay, next let's look at problem 10. What does it say? Okay, we are going to play this trick that by using the curve in exercise 6 at some point. So that would be problem. Okay, so we do that. Okay, in other words, we're going to plug everything in and see how it works out. So here's everything, and calculate f prime. And eventually, when everything comes out, then we do the tangent and the normal. And I once I was done, I checked the answer. The answer is in the back, and this is correct. So that is always good. And finally, problem 11, we're supposed to calculate the arc length, and just plugging it in. This is the arc length. This is about it. Okay, it's a one-line thing because we don't know what f and g are, but so we don't really care what happens to it, right? This is the formula, and if we ever know what f and g are, then we know we can get this to come out. So that's problem 11. So next, let's look at problem 14. We have this curve where it has a singular point, which means x prime equal to 0 at that point. Well, but we still have to find a tangent line anyway. Well, if that is the case, then when you look at this thing, it's got too many t's, okay? T squared, t cubed, goodness, it's way too many. So I'm going to reparameterize it and let u equals to t squared, okay? So then u equals to x1, then x2 is u to the power 3/2, right? And then x3 is now u squared. And that way when you take x prime of u, then we got a 1 in there instead of everything crashing into 0. So when t is 0, u is also 0. So then x prime as 0 is actually 1, 0, 0, and rather than a null vector, which will get us nowhere. So 1, 0, 0 is the tangent vector, the unit tangent vector at the at everything being at the origin. Now that sounds a bit odd, right? So I plotted this thing, being that this is a 3-dimensional object, so we can plot it. And then here's the plot. As you can see, then okay, see, the red thing is the curve, as you can see, and the green thing is my tangent line, okay, 1, 0, 0. Now, the green thing is tangent at the red thing, on the red thing at the origin. It doesn't look like it, does it? You think, well, that doesn't look much. I've seen better tangent lines than that. However, if you zoom it in, okay, here I am zooming it in all the way down to before, the graph before is up to about 1, right? You can see the number 1 in there somewhere, maybe. So if we're zooming it all the way in where it goes down to 0.002, you notice that the red line is tangent to the green line. In fact, the more you zoom in, the more the two lines start fusing together. So this does work, okay? Once you zoom it in, then you will notice it. So that also means that my answer is correct. So that's problem 14. Next, let's look at problem 15. Here it is. And problem 15 asks a very simple question. Here's a bunch of some curve, right? Is this t the arc length? Now, for it to be the arc length, it's very simple. You just need to know that the magnitude of t prime is equal to 1, okay? That is, we need to calculate the magnitude of t prime. Now that sounds easy enough, right? Until you get to calculating it and realize that you're confronted with a giant amount of algebra, right? And look at this. So I started doing that. We just need to prove that the x prime t, the magnitude equal to 1. So let's calculate it. So we're giving x1, x2, x3, so we calculate the derivatives. So far, so good. Yeah, we need to throw x prime of t equal to 1 because of theorem 2, etc. Okay, now, but look how much stuff we're going to be squaring. So to make life easier, then I let w equal to t over square root of t squared plus 4. And plug that in. And because of that, then square root of t squared plus 4 equal to t over w. Okay, and then once I've done that, then x prime of t and x1 prime and x2 primes here and x3 prime all here is looking a little bit better. So once I square them, I got to here, and then eventually got to a bunch of stuff, okay, and then eventually I messed up a little bit, not a lot, okay. What I messed up here is I forgot about the square root of 2, because I wrote it too far apart from the other stuff, so I didn't see it when I carried it down here and had to hunt it down and find it later. But once I found my square root of 2, see, I added which means I had to add a 2 here because I'm squaring stuff. But eventually I was able to, after all this stuff, came up with the x prime of t is equal to this, okay, which does identically equal to 1, which means yes, t is the arc length parameterization, and that is t equal to s. That seems like, yeah, so that just takes a lot of patience to plow through all this much algebra. But once you have done it, you will feel very good about yourself, okay? And that marks the end of this section.